All right, chapter 4, we're going to start a discussion of antiderivatives. So show of hands real quick. How many of you have to take Calc 2? Okay, about maybe a third to a half of you. We will start the discussion of antiderivatives today, but you will not stop the discussion of antiderivatives until you get to middle to the end of Calc 2, because antiderivatives are far more in-depth than derivatives are. Okay, so what we will encounter in Calc 1 are kind of the equivalent, not completely, but kind of the equivalent of what we did with the derivatives in that very first section where they were simple derivatives. So there's no product rules, no chain rules, no quotient rules. There's a minor exception to that at the very end of this section. But for the most part, these are simple antiderivative rules. That said, it doesn't mean that you might not have some algebra to simplify, stuff like that, but it's not the calculus stuff that'll probably catch you in this. It'll probably be algebra if there are things. So we're going to take a look at remembering real quick that everything on the front page here, very first page of your notes here, are writing down derivatives. Okay, so this is going to be real quick. So I want you to fill them in. I'm going to give you like 2 minutes to fill in as many as you can. I'll flip through it for those of you who don't have notes printed so that you can write them down, and then we're going to make sure everybody's on the same page. So this is the first, I don't know, 5 of them, I guess. And after about a minute, I'll flip to the next set, and I'll do the next slide, because I think I've got 2 slides of these. Yeah, I do. Let's take a minute or so and fill in as many of them. Not as many of them you remember. You remember them all, so just fill them all in. Those of you who are using the overhead, can I flip to the next screen yet, or no, not yet? Yeah? Okay. The next ones were the trig ones. Okay, let's see if you have them all written down correctly. I suspect most of you have perfect 100% on this front page. All right, what's the derivative of a constant? 0. It is 0. So this is y prime equals 0. What is the derivative of a linear function? It is a. What happens when we have a constant multiplied by a function? Yes, it's the constant times the derivative of the function. What happens when there's a sum and difference?
You just add the derivative of each.
Yep. Derivatives of each. And then you add or subtract whichever way you have it, those values. And what about the power rule?
It adds to n-1.
Okay, all good, right? Cool. Hot trig rules. What's the derivative of sine?
Cosine.
What's the derivative of cosine?
Negative sine.
What's the derivative of tangent?
Secant squared.
Derivative of secant?
Secant tangent.
Cotangent?
Negative.
Mm-hmm. And the derivative of cosecant.
Negative cosecant potential.
Okay, all good, right? Okay, so what we're doing in this section is we're going to start with things that are on the right-hand side. That is, they are derivatives, and we're going to go backwards. That's what an antiderivative is. Because let's be real, that's what addition and subtraction are to each other, right? They're just undoing each other. Multiplication and division undo each other. Radicals and roots, is that right? Radicals and powers undo each other. This is just another inverse operation. It does have one caveat to it that we have to be a little careful of, and I'll show you what that is. But what you're going to see instead is you're going to see the same kinds of things that we had before, but we're going to be thinking backwards. In other words, if this is what I had, what would my function have had to have been to have given me this derivative? So what would my function have had to have been to give me a derivative of 0? A constant, right? Some number, we don't necessarily know what it is, but some constant. Now the notation for antiderivative, unfortunately, is not quite as observably, it's just not as obvious. It's not as observable as when we do derivatives, we just put the primes on them. What we're going to do instead is we take the letter, whatever it is, and we make it a capital. So if we're looking at a function over here and this had said little f of x, this would say capital F of x. So since we're looking at lowercase y, it's capital Y. Okay, so that's the notation that we're going to be looking at. Actually, I think I'll just leave that there as a reminder. So you're right, it's a constant. And what we're going to use for constants every single time we have them is we're going to use C. Okay, so far so good? All right. What would my derivative have had to have been to give me what would my original function have had to have been to give me a derivative of K?
Kx plus
Okay, so it would have had to be Kx, and then it could have a C. Say again?
Maybe, maybe not.
What'd you say?
The plus C doesn't have to be there to
Right.
give you that derivative.
Exactly. So the C on the end is letting us know that there's an arbitrary factor to what's going on. There could be an additional constant on the end. And that's actually going to show up on every single antiderivative. That's the caveat. Because when we take derivatives of constants, they become 0. And the reason that that happens from a graphical standpoint is because, as you know, derivatives talk about slopes. Well, slopes have nothing to do with where the graph is positioned on the y-axis, right? You shift the same graph up and down, and you have the same slope. It doesn't change anything. So these translations, these vertical translations, can happen, and it doesn't actually affect the slope. So every single time, we're going to put plus C on the end of these. And when we get to it, which is, I think it's next week sometime, we're going to do an antiderivative gateway, just like you did a derivative gateway. And my very first suggestion is going to be that you should write plus C at the top of your antiderivative gateway, because without it, it's wrong. I had one boy, it was a sad day. He got every single one of them wrong because he left off plus C. And if he had plus C on every single one of them, he would have gotten every single one of them right. Every single one. He was a very sharp student. He just forgot, right? So that plus C is really important. All right, so what do you think is going to happen when we're going to do capital Y's on all these. That was a weird looking Y. What do you think is going to happen when we have a constant multiplier? Well, you don't unmultiply, but you undifferentiate it, right? So the constant multiplier K stays the same. And then what do you think is going to happen to the lowercase f of x? Yeah, so it's going to have a capital F of x. And we're going to have a plus C on the end. What about when we have these pieces that are added and subtracted together? You're just going to capitalize them. I know it's going to look like a little bit more interesting when we use actual functions, but we're just going to look at each one of them and go backwards on each one of them. F of x, g of x with capitals. Okay, this is the most interesting one because it's actually got some meat to it. X to the n. Now I want you to think what happens over here with x to the n. We take this n that's there and we bring it down as a constant multiplier, right? And then we decrease the power by 1. So we want to do everything backwards. Okay, everybody good? So what will happen over here is that instead of decreasing the power by 1, we will increase the power by 1. Instead of multiplying by the previous exponent, we're going to divide by the new exponent. Need a plus c on the end, but aside from the plus c part, think about what will happen if you take this expression x to the n over n plus 1 and take its derivative. The n plus 1 would come down, which will then cancel with the denominator, and the exponent would become 1 less, making it n, right? And we'd be right back to where we started with the x to the n. So it's everything in reverse. Add instead of subtract, divide instead of multiply, new power instead of old power. All right, the trig functions are the most fun because they're the most direct. What you will notice right now is that it does not have functions where it says what's the antiderivative of tangent, secant, cotangent, or cosecant. Do you guys notice that? Yeah, it's not there yet. We're going to get to them. It's just not in this lesson. Okay? So what we're doing is we're actually taking exactly everything that's on the right-hand side, except for the negatives, perhaps. And we're just going back to the other side. Okay? So whose derivative was sine? Cosine. Now, do I need a negative? That's the question. I do, because the derivative of cosine is negative sine, and I have positive sine here. So I need negative, and of course I need a plus c. Whose derivative was cosine? Sine. Do I need a negative? No. Because again, if I go backwards, the derivative of sine, the one I just wrote down, is cosine plus c. Whose derivative is secant squared? That is tangent. And tangent and secant have no negatives involved, right? No negatives on those. Whose derivative is secant tangent? That one is secant. And again, there's no negatives involved for tangent and secant. However, the cosecant and the cotangent have negatives involved, right? Cofunctions? Okay. So whose antiderivative is cosecant squared? Cotangent, and it's negative. And whose antiderivative is cosecant cotangent? Yes, negative cosecant of x, yeah, plus the c. Okay, so these are your basic antiderivatives. This is exactly what your gateway is going to be about. That's it. So we're going to do some practicing of particular problems because it's really nice and straightforward for you to write them all down, but we actually have to use them in reverse now too, right? So we've got a bunch of questions to look at today together. And, excuse me, just like we did on the derivative gateway, I'll mention along the way, you could stop here for a gateway. But as we're working for homework, as we're working for quizzes, for tests, things like that, we'll clean things up as those opportunities present themselves. So the first example, I haven't told you about this notation. I'm so sorry. This notation right here where you have a script S right there, that notation actually means to find the antiderivative. The word general here that you're seeing in the middle is because we're going to have that plus c on the end. Eventually, we're going to figure out what the c is in certain contexts, and it's going to be called a specific antiderivative. But right now, all we're going to have is generals. We're going to have plus c on the end of every one of them. So this notation is just saying find the antiderivative. Now, you'll notice that there's a script s at the beginning and there's a dx at the end. It's kind of like the beginning and the end of a parenthesis. There's either both of them there or neither one, okay? So once you eliminate the script s at the beginning because you've taken the antiderivative, it correspondingly eliminates the dx at the end. Now let me explain what the dx means. The dx is telling you that the variable you're using is x. Or if it were du, the variable was u. If it were y, the variable is y. And you might be saying, well, duh, look at the problem. So the reason it matters is because when you take Calc 3, and I know at least a couple of you will because I know what your majors are. Calc 3, you do something called multivariable calculus. So a particular problem will have more than one variable within it, okay? So you got to know which one's considered the variable at which time. So this is actually a notation that's introduced really early on for practical purposes later, okay? So I just want you to know there is really a reason behind it. Right now it feels kind of silly. That's okay. That happens a lot in mathematics where you don't exactly know why you're learning a piece of it until you need it a couple classes later. This is one of those things. So these two pieces will be eliminated at the same time that we put the plus c on. So sometimes I have students remember that too. I have a plus c or I have the dx. I don't have both. Okay? So the part that matters to us is the part that's sandwiched in between. I was trying to highlight. The 2x and the minus 3x squared. Okay, so the 2x. So normally when I would see 2x, right, or anything with an exponent, I take the exponent down and multiply, right? So what I want to do instead, I've got an x and I need to increase the exponent by 1. So the constant multiplier stays there. That's a 2. That's the constant multiplier rule. The exponent on the variable increases by 1, so it will become a 2, right? It is an understood 1 at the moment. And then I divide by my new exponent, which is 2. So the 2's are going to eliminate themselves in a moment, but if you were doing a gateway, you could leave it like that and be fine. We're going to do the same thing to the next piece. The sign stays the same. That's the sum difference rule. Constant multiplier stays put. X squared becomes x to the third, and I will divide by my new exponent.
I have a question.
Yes.
If we could have done that without showing those steps, do we have to show the steps?
So I think what you're saying is if I recognized that this 2x came from x squared and 3x came from x cubed, is that okay? And the answer is yes.
Okay.
Generally speaking, the coefficients are not so friendly to do that. They just were on this one because it's the first problem.
Okay.
So most of the time, you're not going to see it like that. Yeah. So, but it would be okay. I need plus c. This is what you could stop with on the gateway, no matter what the coefficients in the front were, if they were messier especially, okay? For the purposes of what we're doing right now and cleaning things up, that would be silly to stop there, right? There's multiplication and division by 2 in the same piece. I'm not going to leave that like that. That's silly. So these are going to eliminate, as are these. So we end up with x squared minus, x cubed, and then plus c. How could you check to make sure you have the right answer?
Take the derivative.
Take the derivative, right? Everything's simple rules that we're working with. You can go backwards, the same direction you've been going now for 2 months with me, all the time if you want to make sure you have all the pieces right. Any questions on that one? Yep.
Will it always be plus C?
Yeah, it's always plus c because c could be a negative, so it doesn't really, we don't need it to differentiate. Is it a positive c or negative c? C itself will have a sign, and we just use the sign, so we just write plus c on all of them. Yep. Okay, number 2. Number 2 doesn't exactly look like the form I'd like for it to be in. Any ideas of what form I might want to rewrite it in to be more helpful? X to the negative 6th. And I still have my minus 2 here. So this is a more helpful form, just like it would be if I were taking a derivative, right? It would. So I need to take the x to the negative 6. Well, there's no constant multiplier, so I'm just going to write the x down. What will my new exponent be? That plus 1, so negative 5, right? And then what did you say, Nick?
Over negative 5.
Over negative 5, yes. Okay, is that all right? So again, for the purposes of the gateway, that's perfectly fine. We're going to adjust it here in a minute. How about my 2? I know it's negative, so I'll keep the sign, but 2x, right? So constants will now have an x reattached to them. That's what will happen, and I need a plus c. So again, gateway purposes, we're done. We're not going to leave it like this in this problem, not because it's necessarily wrong, but because the problem didn't start out that way. The problem started out with a positive exponent in the denominator. We're going to go back to positive exponents. So we're going to shift that back to the denominator, which would leave a 1 on top, negative 5x to the 5th on bottom, minus my 2x, plus my c. So this is our as cleaned up version as we need at the end.
You might have said it already, but why didn't we write the negative 6 before the x?
You mean when we took the antiderivative? Because we are working backwards. So we always add a value to the power and divide. Taking derivatives, we multiply and we subtract.
Okay.
That's the difference.
Yeah.
We're going to add and divide. It takes a minute to adjust. And by the end of this section, we're going to intermix some of these pieces at the same time, and it's going to be amazing. You guys are going to do fantastic. The culmination section. Okay, how about this one? Not in the most helpful form. How could I rewrite this to be more helpful?
So negative 1 times x to the negative 1 half.
Okay, say it louder for me, Nick.
X to the negative 1 times x to the negative 1 half.
That's a great first step. Then what could I do? Is everybody okay with that? Do you see where those pieces came from? What could I do to consolidate them together? Okay, so not multiply, but add the exponents together. Properties of exponents, I would add the exponents together. If I added -1 and -1/2, I realize I'd have -1.5. That's not really the most beautiful thing when we're actually working in mathematics. My 7th graders think that mixed numbers are wonderful. I disagree. Yeah, -3/2 is much better. Okay, so for computational purposes, improper fractions are way easier to work with. This is sort of the most compacted and clean form that we can work with for finding our derivatives or our antiderivatives, either direction, actually. So what would my antiderivative be if I have x to the -3/2? Okay, so x to the -1/2, and then what? Over -1/2 plus c. What's that? We'll do that in just a second. In fact, you're right, Joel. So in terms of like absolutely just applying the rules the way they're stated, right? We add the value to the exponent, we divide by the new power, it would look like this. We could leave it like that and it'd be fine. We're not going to leave a fraction inside of a fraction. That's not cool. And we're also not going to leave that negative exponent on top. And we're also not going to leave it as a negative, or as a square, we're going to rewrite it as a square root because it started out as a square root. So we're going to do a lot of pieces to clean this up. The first one I'll do is the one that Joel mentioned. Dividing by -1/2 is the same as multiplying by -2. So this is -2, right? Being multiplied by it. And I'm going to go ahead and put the x to the 1/2 in the same step back in the denominator. Okay, so made by exponent positive, instead of dividing by 1/2 and multiplied by 2, negative, and we have this. And then we will rewrite this with a square root of x instead of a 1/2, simply because that's how it began. If it had begun with exponents that were or like fractional exponents, we could leave it like that. That would be fine. But this one began with radicals, so we're going to put it back in radical form. Yes, Shelby?
Another reason, like, consolidating, isn't that because n cannot equal -1%?
Yeah, so we didn't make a mention of that. And let me actually mention why that's the case. I'm glad you brought that up. I kind of brushed aside it. Which slide is it on? I don't think I have it on my slide. That's probably why I did it. Which one's it on? Do I not have it written down? Oh, it's a simple power rule. I just don't have it written down right here. Okay, there is a property here that says that n cannot equal -1. It's in your notes. Let me show you why it can't, because I want to show you what happens if it did. And then I'll answer your question more directly about how that isn't quite what's going on here, but I know why you're seeing it. So if you in fact had x to the -1 here, right? Let's see what would happen. Well, it says I would add 1 to the power, and then I would divide by my new power. And what do you notice? There's a 0 on the bottom, right? That's a problem. In particular, this kind of a function, which is the same thing as 1 over x, has another antiderivative form. It's just not with the power rule, and you get to it in Calc 2. So it involves logs, and I'm spoiling all the fun for Calc 2, but you will have fun with Dr. Drake, and it'll be great. It's logs. Logs come into play when that happens, so we won't have that situation. The more pressing issue on this one of why that wouldn't be the case is because we have a product. So we don't have anything to deal with about what happens when there's a product rule. So we have to consolidate so we don't have a product going on specifically. Yeah. Thank you for bringing that up. I need to get that into the slide notes so that I remember to say it when I see it there. Okay, number 4. Oh, it's a product. I just said we can't have a product, right? Well, isn't that funny? All right, so we got a product, and that's a problem. And on your gateway, we encountered this originally, too, when you had some products. And you could use the product rule, and some of you did. But you could also use some simple algebra if you wanted to clean things up. Well, we don't have a product rule for division. In fact, that's exactly, or for antiderivatives. And that's exactly why you spend so much time in Calc 2 working with antiderivatives, is because there isn't a product rule form. And so you have to figure out, well, what happens when I have a product that I can't actually simplify? So we're only going to be working with ones that we can. We can simplify this with algebra tools, right? Of course. This is the stuff that my college algebra students, even some of my intermediate algebra stuff that students will be doing pretty soon, where we're just multiplying this out. So we're going to do first, outer, inner, and last, and we're going to distribute and clean things up so that we can consolidate. So we have 3x squared. My inner is 3x, my outer is negative 2x, so this is plus x, and then minus 2. So anytime you see something that looks like a product rule, you have to combine pieces somehow. The last particular one that we did, right above this, we're on this particular slide, we were able to use properties of exponents. Here we're able to use distribution. And then we're going to do the same thing. So it's the antiderivative of 3x squared, x cubed, and if you recognize it at this point, which we might have the case too, that's great. What about the antiderivative of x? Okay, so we increase the power, divide by the new power. Antiderivative of negative 2, negative 2x, and then plus c. Okay, and I don't have any simplification to do here. There's not anything that combines. There's not anything that rewrites nicer. If you really hate the fact that the x squared is over 2 and you want to write it as 1/2 x, fabulous, go for it. This doesn't really change anything. So we're good to go at that point. All right, let's look at a few that involve some trig. I know those are your all favorites, right? Okay. Well, we don't have a lot of options here. They have to end up looking like these, right? If they don't look like these, we have nothing that we can do. So we have to get them into some kind of form like this. So as we're looking at this first one, number 5, this piece looks familiar. That's the trig piece. So let's start with the 1 at the beginning. What's the antiderivative of 1? X. What is the antiderivative of negative cosecant cotangent? Positive, cosecant x. Then what? Somebody said plus c. Good. Remembering those plus c's. So if you're getting something robbing a WebAssign, probably your first step to look at is make sure I got the plus c in there. It's an easy thing to forget. Okay? And you're done. There's nothing else to do. Okay, number 6 isn't quite so straightforward as all that. Right? I mean, it isn't. But there is a trig property present there that you should know. Okay, so the property that you should know is a Pythagorean identity. And again, I've encouraged you to print them out before, but maybe you haven't utilized that and didn't need to. If you don't remember the properties of trig that we're going to utilize, I have a handout printed inside of Canvas. Posted inside of Canvas, you can print it out. This is a Pythagorean identity. The Pythagorean identity says that sine squared of x plus cosine squared of x equals 1. So nod your heads. This is the most familiar of the 3 Pythagorean identities. We have a version of that in the denominator. I have 1 minus sine squared, so I have this piece moved over, which means I have the denominator as cosine squared. So this will rewrite as sine of x over cosine squared of x. Now that may not be exactly useful, but it's actually quite a bit better. And the reason it's quite a bit better is because I don't have addition and subtraction in the denominator. Addition and subtraction in denominators make things complicated. They just do. So if I can eliminate addition and subtraction, I'm in a better position than I was before, right? So as we're looking at this now, there is one more identity that would be helpful to know, or we can deal it with another. There's a couple of different ways we could do it. So anybody see an option of something you could do to consolidate, if you will, the sine and the cosine squared? Okay, so yeah. Say that again, Joel. I heard you first.
So sine over cosine would become tangent, and then you could multiply it by 1 over cosine, which is secant.
Okay, so if you break the cosine apart into 2 pieces, it's cosine and cosine. You write the sine over one of them, and you write the 1 over one of them. And I can do that because it's multiplication, right? The addition and subtraction doesn't allow for separation of the denominator in that way. But in times of multiplication, which this one is, because the power, I'm allowed to do that. So this, I think, is the cleanest way to do this. If you don't see it right like this, you could also change your cosine squared into secant squared in the numerator and manipulate with secant squared. I don't think that's as direct of a process, but it is possible. So just like you had mentioned then, Joel, the sine over the cosine is tangent, and 1 over cosine is secant. Okay, so notice every time I write the script s at the beginning, I write the dx at the end. Your work should look like that as well. I will be looking for that on quizzes and on tests, okay? I know WebAssign will probably automatically just stick them in there for you or something, but they need to have the beginning and the end until we've actually taken the antiderivative.
What about the other ones that we did earlier that weren't dealing with trig?
We didn't have that. We did a little bit of manipulation over here, just changing the pieces on the inside.
Script stuff for those?
Well, I was just using them like scratch work.
Okay.
Here, I'm doing them more structured, like equals. This equals this equals this. Does that make sense? What I don't want you to think that somewhere along the way is that over here, what I circled in the left actually equals something over here on the right. These don't equal. They only equal if I have the script s in the front and the dx at the end. Okay? Does that make sense? So this equals this, and it went down like that. Oops. The parts that I've circled in red are more like scratch work for me rewriting the pieces in between. If you want to be more precise and make them equal, you could, Abby, and you could put the script s here, the dx here, the script x here, the dx here, and then they would all be equal. Okay, so either make it look like it's scratch work, set it to the side basically, or if you're telling me things are equal to the next thing, equal to the next thing, make sure they really are. What's the antiderivative of tangent secant? Yeah, that one is secant of x plus c. Good. So some trig simplification is going to show up. You're going to have to do some pieces of that, but nothing expansive. No, there's no double angles, there's no half angles, there's no sums and differences of angles. We're not in trig. Okay, we don't need all of that for the purposes of what we're doing right now. You will need more of that in Calc 2 for those of you who are taking it, but they'll cover it again and remind you of those pieces when you do need them. For right now, we're looking at those three, which are the quotient identities, reciprocal identities, and Pythagorean identities. Those are the ones that are on that handout. All right, there is a little bit of change on these last two questions. This one actually asks you to find a particular solution. Do you remember the earliest on I said that we were finding, whoa, hang on just a second, I clicked on a button. Let's try that. General antiderivatives, and eventually we'll be asked to find specific antiderivatives. Well, they are going to pop up at the end of this lesson for the first time. So what does it mean to find a particular solution? Well, it means they give us an extra piece of information at the end, namely, this is what it is on this one, f of negative 1 is equal to 3. And what that will allow us to do is it will allow us to figure out what is C. Okay? So when we're working with general antiderivatives, what we're doing is we're going backwards to create the structure of the original graph. But we recognize that the structure could be shifted up and down vertically anywhere along the y-axis and have the same shape, right? Once we fix a point in space, we can no longer shift things around anymore. We're stuck, and it actually sticks the whole graph where it actually would be. Okay, so the process actually looks a lot like what we were doing before with one little piece on the end that's an algebra piece that you will know how to do. So let me show you. They give us f prime of x. Notice, it says f prime of x. So when I take the antiderivative here, I don't use a capital. I don't see a script s and a dx because the notation is actually written so that I can just go back to f of x because they told me f prime. Okay, happens sometimes. It's another way of seeing it. We're doing the same thing we were on the previous problems. 4x squared. What's the antiderivative of 4x squared? Awesome. 4x cubed divided by 3. Okay? Plus c. Okay, everybody good? That's the antiderivative. If the problem started out like this and the directions at the top simply said, find the general antiderivative, the da-da-da-da, whatever, and it didn't have the parts that are highlighted in red on the equation, right, the f of negative 1 equals 3 business, we would be done. So what does it mean now? Well, it means that we use this piece right here. We plug in 3 for f of x, and we plug in negative 1 for the cubed. If we could have simplified that, we would have, by the way. I didn't mention that because it couldn't simplify. And the only thing I don't know in this equation now is c, so I can find it. So we're going to do a little bit of simplification with fractions here. I have 3 equals 4/3 plus c, and then I Thank you, because it was cubed. Yep, negative 4/3. So I add 4/3. So what is 3 plus 4/3? 13/3. So we have solved for C, which we needed to do, but we haven't answered the question yet. The question said, find the specific antiderivative, right? So I go back to this one right here, and I'm going to write it out. F of x equals 4x cubed over 3 plus 13/3. And if I were to take that derivative, would it get back to 4x squared? It would. It would. Is that all right? The next one's the most interesting. Double primes. Okay, so notice what it did here is it took a second derivative and it gave you information. But you know that the relationship between a function and its derivative is the same as the relationship between the derivative and the second derivative, right? You just take another derivative. So we're going to be going backwards twice. That's all we're doing. So we're going to take this equation right here and first go backwards one time. Well, it's an f double prime, so going backwards once is going to give me f prime. What is the derivative, antiderivative, excuse me. I'm going to do that for a while because we've shifted gears. What is the antiderivative of x squared? X to the third over 3 plus c. Now it's a race to say the plus c first. It's awesome. Good job. Okay. Now, sometimes I'm not given enough information to do much beyond that. All right? What I mean is I'm given this wonderful piece of information telling me that the derivative's value at 0 is equal to 8, and I'm going to use that here in a moment. It is possible that when I'm given this particular problem, instead there's no prime here, and it actually just tells me 2 f of x values. Well, if I did, I would just take the antiderivative again. And I would actually, I'm going to show you what I would do just because I want you to see it, because there is one that shows up later on. And you'd say, okay, well, now I need the antiderivative of x cubed, which I'll get there in a minute, and it would be x to the 4th over 12, right? It's 3 times 4. The 3 was already there. The 4 is there now, so it's a 12. And this c would have a c times x. And then I need a plus c, but the c's might not be the same, so I need to be able to differentiate them, right? So what I would do is I'd call this one c1, and I just call this one c2. Now that's not what we have in this problem because we are given information to be able to actually deal with the antiderivative, the antiderivative, the f prime part of it. So I'm going to go backwards here, but I just want you to see that you can actually be asked to do one step further and have 2 c values. Because if I have an equation and I have the pieces of information that are given, this one doesn't work because I screwed it up, of course. I can actually still find both of those pieces of information if I'm given those from that perspective. So let's go backwards here. I'm not going to need this piece because it'll change here in a second. I'm just going to shift this down because it won't change. Let's find out what is C1, which was just our C. Okay, well, it told me that f prime of 0 is equal to 8. Okay. Well, the f prime is 8, so that's the left-hand side. 0 is the x, so that's 0 cubed over 3. What will c be? It's 8. So this function, f prime, is actually x cubed over 3 plus 8. So far, so good? So coming down here then again, I already did the first part, right? X cubed over 3 is now x to the 4th over 12. Plus what? 8x, because I found out that it was 8. Plus c, thank you. And we recognize this c might not be 8, right? I mean, it's just another c. It's another random constant. If it bothers you to have 2 c's in a problem, call it something different. You can call it k if you wish, or you can call it c2 if you wish. It doesn't matter. But if it doesn't bother you, that's fine too. Just recognize it's probably not 8. So if we want to, we can rewrite this as 12. That might be a little bit prettier to work with. And then I'm left with this last piece of information. F of 0 is 4. So I have 4 on the left. I have 0 to the 4th over 12 plus 8 times 0 plus c. What's c? It's 4. So my final answer for my original function is that f of x equals x cubed over 12 plus 8x plus 4. Yes. Thanks. All right. Are all the pieces there now? Excellent. Okay. So we are finished for today, just a few minutes early. WebAssign for 4.1 is up and out there, so you can take a look at that for this evening, due on Wednesday.